That's the best draw. That's insane. It's a hard class. Okay, I dropped it to class. Like, okay, I feel like physics, econ, that's gonna actually affect my GPA because like if I did an AP class, the weighted you're right to go. It doesn't matter. I know. They're not gonna kick you out as soon as you call. And I have a scale in my 60s. We drop all your clubs. I was 53 on my last physics test. It's okay. Maybe he gets. I probably got way worse on one of the class tests.
Right. Guys, I'm picking problems from problems we've already done. So I have some additional handouts of blank copies of the help session review packet. So you can pick one of them if you like. We'll start with page 1 here. We'll just practice one problem with a quick trig related rates. So the triangle above, the theta is increasing at a constant rate of 3 radians per minute. At what rate is y decreasing in units per minute when x equals 3 units? So we have to start off with a trig function, but let's see if we can gather some information first. Theta is increasing at a constant rate of 3 radians per minute. We know that's talking about rate of change of theta, so we can call this d theta dt. Constant rate of 3 radians per minute. This is a positive value because we know theta is increasing, so positive 3 radians per minute. At what rate is y decreasing? So we're looking for what? dy dt, okay? When x equals 3 units. Okay, so those are all the information that we have. Okay, so we're looking for dy dt. We have information about x, and we're looking for, or we have information about d theta dt. We have kind of limited information about x, and we have more information about y, or also we're looking for dy dt. So, and anytime that we can hunt for a constant, that's always going to make things easier. So we're, here we're kind of headed towards using a trig function that's going to hit theta, y, and 5. So which trig function should we choose? Cosine, right? So cosine is going to allow us to involve theta. It's going to allow us to involve y, which we need because we want dy dt, and also take advantage of one of the constants. So we can say cosine theta equals y over 5. Okay, get it ready for my derivative process. And call this 1/5 times y. Now derivative. Okay, so cosine becomes negative sine. 1/5 y becomes 1/5 dy dt. Just power rule. Okay, dy dt, that's what we're looking for. So it's good to have that variable there. D theta dt, in this case, we do have that information, so we can fill that in. What piece do we still need to find on our own? Okay, say it again. Sine of theta, right? Not theta, not just theta. We want to find an entire ratio to replace for that sine of theta. So if we kind of redraw our triangle and fill with numeric values, we know this is at this moment in time now, hypotenuse is 5, y is, see, we know x is 3. So Pythagorean theorem will help us get to that third missing side, a squared plus b squared equals c squared. So the missing y value at this moment in time must be 4. So sine of theta, what's sine of theta going to be? 0.5, right? Opposite over hypotenuse. So that will allow us to find the replacement that we need. It's the last piece of information that we need. and we can just solve for dy dt now. So the negative carries over. d theta dt gets replaced with 3. And then we're looking for dy dt. So I want to solve for dy dt, so I want to move that 5 over to the left side. Dividing by 1/5, the same thing as multiplying by its reciprocal, so the reciprocal would be 5 over 1. Sorry, 3/5. The 5's cancel out. I can make it just -9. Okay. Any questions here? All right, let's do the particle motion problem. We've done this already, but it's good to get that additional practice. Okay, a particle moves along a horizontal line so that at any time t, its position is given by x of t equals 2 pi t plus cosine of 2 pi t. Find the velocity. So to find the velocity, I need to find the derivative. So let's look at this one at a time here. V of t equals. All right, so what does 2 pi t become? It's just 2 pi, right? The coefficient is going to stay. The variable is going to drop out. All right, and then cosine of 2 pi t. Let's think about the derivative for cosine. Cosine of u becomes negative sine of u times u prime, so times 2 pi. Okay, any questions so far? I'm going to do some little bit of cleanup here just to kind of rearrange things, but that's our derivative. All right, next up, find the acceleration. So acceleration is the second derivative, right? PVA, position, velocity, acceleration. All right, so let's find acceleration. A of t equals, all right, 2 pi becomes 0. 2 pi sine of 2 pi t. Do we need to go through product rule here? We could, but do we need to? Because 2 pi is just a number, right? It's not a variable. It's not like x. It's not like t times sine of 2 pi t. 2 pi is just a coefficient. It'll just tag along to whatever the derivative is. It's really the sine of 2 pi t we got to worry about. So sine of 2 pi t becomes cosine of 2 pi t times 2 pi again. All right, so another u prime is going to show up. And just to clean this up, the 0 can go away. The 2 pi and 2 pi are in the same location. They're both outside the cosine, so I can merge them together. Let's say part C wasn't here, okay? Let's say I completely eliminated part C, and I just jumped directly to part D. When is a particle moving left, moving right, justify with because statement? So to get to this point, what information do we need? We need to first figure out when the particle is at what? Rest. So even if this part wasn't here, and I ask you for this, you'll still need to get all this information, right? You have to populate your velocity sign line. You got to find your critical point, populate it, test your intervals, right? So, but right now I have C right here as a way of, showing that's kind of like the next step towards D, right? Because we got to create our velocity sign line. Okay, but first, particle at rest, that's when velocity is 0. So we'll set velocity equal to 0. Okay, I'm going to move that negative 2 pi sine 2 pi t to the left side, just so I can get both terms to be positive. All right, piece by piece, I'm going to see if I can work my way down to solving for t. What would you do first? Yeah, let's get that 2 pi out of the way. So get that coefficient to go away, and we can get that right side to clean up as well. 2 pi over 2 pi is just 1. Now, this is a little messy, right? You got that inside portion inside the sign that we want to get to, but we also want to solve for t. So first things first, let's just try to get this parentheses isolated. Let's move that sign. So if I want to move that sign, it's going to become what on the other side? Inverse sign, right? So we're kind of piece by piece, kind of removing things away from what we want to solve for. Right, so we want to figure out where is sine of theta equal to 1. So where's sine equal to 1? Over 2. Now we got to divide by 2 pi here eventually. We want to find out all the values up to 3. So let's go a couple of intervals out, right? Pi over 2 is the only value from 0 to 2 pi where sine is equal to 1. What if I wanted to find more coterminal angle? Add 2 pi, right? So if I add 2 pi, I get additional values that I potentially would need, because if I shrink it down, I don't want to miss out on the solutions that are closer to 3. So adding 2 pi is the same thing as plus 4 pi over 2, just so I can get my denominator matched up nicely here. So what's next? Pi over 2 plus 4 pi over 2 is 5 pi over 2. Let's keep going. Let's go a few more just so we can make sure we cover everything. What's next? 5 pi over 2. Okay. I want to solve for t, so I'm going to divide by 2 pi. Dividing by 2 pi is the same thing as multiplying by 1 over 2 pi. So that isolates my t variable here. Multiply across. What's this first term going to give me? 1/4. The pi's cancel out. The 2 times 2 becomes 4. Next up. Just, yeah, 5 over 4. Next up. 5 over 4. Next up. I know I've gone too far when a t value is greater than 3, right? And in terms of denominator 4, 3 is 12 over 4, right? So anything less than 12 over 4, I want to keep. Anything greater than 12 over 4 is outside my interval. So I have my t values. And if I did not expand it out, then I would only be getting 1/4. I would be missing out on the additional solutions that would reach up to 3. Okay, any questions there? These are finding particle values where a particle is at rest, but these are also critical points that's going to help us populate our velocity sign line. Okay. So part D, when is particle moving left, moving right? We have to still create our velocity sign line because we need to be able to populate the sign line, test each interval, get our positive negatives on our sign line going before we can read it, right? So we have some more work to do before we can interpret our intervals. Okay, so here's my velocity sign line. I'm going to clean this up. I'm going to factor that 2 pi out. Just think it'll make it easier when I'm trying to evaluate. Okay, so I'm going to start at 0, go to 3. Those are my endpoints. Okay, so I'm going to find some fractions here that can fit inside these intervals here. So I'll choose 1/8. 1/8 is less than 1/4. Between 1/4 and 5/4, I can just kind of increase my numerator here until I find something that is easy. So if I do 1/4, 2/4, 3/4, how about 4/4, right? 4/4 is between 1/4 and 5/4, and I think about 4/4 is that's equal to 1. That's nice. 5/4, 6/4, 7. So I can just pick anywhere from 5/4 to 9/4. What about 8/4? 8/4 is 2, so that should be easy to plug in. And then 10/4 to 12/4. I'll just do 10/4 or 11/4. Okay. So if I plug 1/8 in for t, I get sine of 2 pi over 8. Sine of 2 pi over 8 is the same thing as sine of pi over 4, right? Sine of pi over 4 is root 2 over 2. That's around 0.7. All of your unit circle values are less than 1. Okay. So 1 minus a value less than 1 is going to be positive. So I know that my interval is going to be positive here. If I plug in 1, sine of 2 pi is 0. 1 minus 0 is positive. Plug 2 in, sine of 4 pi, that's still positive. But still 0. 1 minus 0 is still positive. 11/4, I get, what if I did 10/4? Then I will get 5 pi, and 5 pi is still 0. So it just seems that in this interval, my particle is either moving to the right or it's at rest. Right, so it moves to the right, it stops, moves to the right. So here, this particle is never moving left. It's only moving to the right. So if we can write our because statement, we can say particle moves right. And notice 0 and 3 are not places where the particle is at rest, right? If I plug 0 and 3, the particle is still moving. So we're going to have to include the endpoints in our interval. So we're going to say from 0 to 1/4, 1/4 to 5/4. Now everything in between is parentheses because these are actually places of rest, but the endpoints are not. Okay? Because velocity is greater than 0.
On the test, the sign line will oscillate, right?
I'm sorry?
On the test, the sign line, will it oscillate?
You have to test them. Yeah, that I can't guarantee that your particle is going to oscillate, but your curve sketching will oscillate. Particle never moves left. Okay. Huh? Yeah, exactly. If there's nothing, now, if there was an interval moving left, you would say because velocity is less than 0. All right, so this process is important. Setting velocity equals 0, critical point, test your interval, test your velocity sign line. Positive is moving right, negative is moving left. Okay. Everybody okay with that process? Okay. Let's go to the next page here. Okay, let's do a couple of derivative problems here. This one here is find dy dx. Let's list out the processes that's involved. What's involved here if I want to find the derivative? Implicit, okay, because you see kind of y's scattered across your problem here. What else? Product rule. Okay, so I want to let you know, students typically have a hard time identifying product rule because usually the problems are not going to be set off in parentheses where you can see two distinct terms in parentheses. If you see two different variables, that's an indication that this is y times secant of x. This is product rule. Right? So recognizing product rule, sometimes some students will just jump directly into a derivative rule, or they will put these two derivatives next to each other and call it a day, but we got to go through product rule, recognize the need for it. Okay, so good, product rule here. All right, so let's start building our derivative here. Okay, f prime, so y becomes 1 dy dx. G is that secant of x. Back to f. G prime, what's secant of x's derivative? Secant of x, the x. Okay, so that completes our product rule for that left side. Okay, right side, keep going. 12 becomes 0. Negative 3y becomes dy dx. And then 5x squared becomes 10x, right? So a good indication as to making sure whether you've collected all your dy dx's. Look at your original equation. How many y's do you see? 2. So you're expecting 2 dy dx's, and we do get that. All right, so now we have 4 terms here. You got that dy dx secant x, you got that y secant tangent x, negative 3 dy dx, and 10x. So we want to just, the calculus is done. Now we're just rearranging, adding, subtracting, dividing to try to get dy dx by itself. So I see my dy dx terms. I want these two together so I can collect their dy dx's. So I'll put them together on the same side. Hey. I have another one of these packets. Half filled out. All right. Okay, I can factor out dy dx. I divide both sides by my parentheses. Okay, questions? Okay, let me use this space to do a problem that I have up here on the board. So I'm going to use this space for this problem. So I'll call this number 4 here. Let me copy this down real quick. That's the bottom one, the x equals 2y arc sine. X equals 2y arc sine 3x minus sine 2x to the 4th. So if you can just copy that problem down, we're going to try this one. It's not, yeah, it's just made this for us to try. Okay, so what do you see? What's involved here? Implicit, good. What else? Product rule, good. So recognizing the 2y arc sine at 3x are two different things. And there's chain rule, right? That sine 4 2x, we got to be careful with that. Take the time to rewrite it, get that bracket to show up. I'm going to rewrite this problem to get this a little bit easier for us to know what to do. Okay. Okay, so I know there's product rule coming up here. X becomes 1. F prime g plus f g prime. Okay, 2y becomes gets to dy dx. Right, if you look at your original equation, how many y's do you see? Only 1, right? So there should only be 1 dy dx that pop up. All right, g function. Back to f. Okay, arc sine 3x. We got to recall these new derivative rules, right? These are the ones. There's 3 unique ones: the arc sine, arc tangent, arc secant. They all involve u prime. They all have 1. They all have u squared. We just have to know what order involved, right? So arc sine is the one with square root in the denominator and 1 minus u squared. I heard a student say this yesterday. They said that what helps them remember is there's a s, so that reminds them that there's square root in the denominator. Okay, so we got to do u prime over square root of 1 minus u squared. So my u value is 3x, so therefore u prime 3x becomes what? 3. Square root of 1 minus u squared, so 1 minus 9x squared. The reason it's 9x squared is because we're squaring both 3 and the x, right? Okay. I'll clean that up in a second. All right, everybody good so far with product rule and that arc trig that we took care of? All right, we said that this is chain rule, so chain rule for that last portion here. Got that outside and inside going on. Okay, so that bracket to the 4th, we can find the derivative first, and then we can follow that up with the derivative for sine of 2x. Okay, so outsize derivative, what does that become? 4 to the third, keep the inside alone. So check that off. I took care of the outside derivative. I'm now moving on to the inside derivative. It's going to be in different space. We don't want to put the derivative inside here, right? So they're both going to have their own space for their derivative. Okay, sine of 2x becomes cosine of 2x times 2. Okay, so we just want to get this dy dx by itself. So really just have to subtract this over, move the 1 over, kind of clean things up a little bit. Okay, so. Final step, divide that -2 arc sine 3x over to the right side. It's not pretty, but as long as we get dy dx by itself, that's all we really care about. Yes. Yeah, if your signs are different, that's fine. If this was negative, this is positive, this is positive, this is positive, that would be the same variation or different variation of the same answer.
In the brackets.
That's fine. Yeah, just want to quickly go over curve sketching. I know that I keep doing this problem, but your problem will look like this, so that's why I keep bringing it up. Yesterday, I did this in page 6 in your packet, curve sketching problem, and we talked about how here's the process, right? You find the derivative, you set your derivative equal to 0, you find your critical points, you find your appropriate critical points, and you place them onto your derivative sign line. You test your intervals, but I'm letting you know that your slope is going to oscillate. So if I can find 1 or 2, then I know the third one is going to be a different sign. So, and these are important because if I can find the relative max, relative min, I know those are going to be a potential absolute max, absolute min, absolute max, absolute min on my graph. So I want to be able to find those or ballpark those y values so that I can also put them onto my graph. So we talked about yesterday that once we populate our slope sign line, we can conclude whether we have a relative max, relative min. And then we move on to our second derivative function, right? Set your second derivative value function equals 0. And now you're finding critical points for your second derivative sign line. And these are now potential points of inflection. And again, you pick values in each subinterval to test against your second derivative function. Positive is concave up, negative is concave down. Now, these y values are not as important. If you know it's a point of inflection, you can still just kind of ballpark where they are after you've sketched your initial version of your graph. So the most important points, though, are your endpoints and your relative max, relative min. I'm going to take the time to place them, insert them back into the original function, and just make some estimations. So whenever you see pi, I'll say, hey, replace pi with 3 and use that as an estimation to ballpark your value. I know you don't have a calculator, but you're just going to try your best to approximate down to something that you can actually put on paper. Okay. If it's a little off, it's okay. So in this case, my endpoints are negative 0.5 and 2.5. If I insert negative 5 pi over 6, I'll tell you, hey, for root 3 over 2, use 1 or use 0.7, something like that. And once I have my ballpark values, I can, the most important points are my endpoints, my relative max, relative min, because that's enough for me to kind of trace my graph, even though I don't know the curvatures of my graph. Okay. So once I have my graph going from my endpoints and my relative max, relative min, then I can go back and kind of imagine where my points of inflections are, right? So point of inflection is at negative pi over 2. In that case, this is somewhere between negative pi and 0. So I'm just going to plot that point. My other point of inflection is at pi over 2, so it's between 0 and pi. If I plot those points there, I just connect the dots, make sure I match my concavity here, concave down, followed by concave up, by concave down. Absolute, and then to find absolute max, absolute min, you just have to look at your graph, right? Absolute max is your highest y value. Your absolute min is your lowest y value. Yeah.
On the graphing, will it always oscillate?
It oscillates, yeah. Okay. Right, derivative rule. Let's see if we can recall our derivative rules. So find any blank space that you can find. Give myself more space here. So these are the ones you gotta make sure you know. Okay, so sine, and cosine are just, they're just involve each other. Tangent and secant, they involve each other. Cotangent and cosecant involve each other. All the C functions produces negative derivatives. Okay, arcsine, arctangent, arcsecant. They all have u prime in the numerator. They all have 1 and u squared in the denominator. I start off with that arctangent, which is u prime over 1 plus u squared. Then I move on to the arcsecant, because I know that I got the absolute value of u, I got the u squared minus 1. I know they're next to each other. And then my arcsine looks a lot like this. It's got the square root, but the order is just a little bit different. Okay, so I'll see if you guys have any individual questions.